Okay, so now to wrap up second order differential equations and higher, we're going to be talking about one main application in control systems, specifically when we are talking about transfer functions. Now, the standard model for a control system is we have an input go into a summer and outputs an error function, E of S, and this is R of S. This error function informs a controller, GC of S, which then informs the plant on how to control and maintain an ideal behavior, GP of S. And this goes into some kind of output. The part that makes it a control system is the feedback path, which is modeled by H of S. And this goes back in negative feedback, like so. Now, if we were asked the closed loop transfer function for this, the closed loop transfer function is just going to be, in general, GC GP divided by 1 plus GC GP H. Now, the realm of control systems is a broad and diverse one, but when we are discussing about it, it is more important to talk about it in the scope of Laplace transforms. However, just in general, we always will see differential equations when we are modeling control systems, mainly because we have to use it to get an idea of the relation between the output and the input. And that relation is modeled by what's called a transfer function. This is called a transfer function. It is one way to relate, or it is the way to relate an input to an output. And actually, by definition, this is equal to the output, or the total output, divided by the total inputs of a system. So, for example, if we were to ask ourselves, or if we were to say that, let's say this transfer function is some kind of function, I don't know, like s plus 1 divided by s squared s plus 2, then this is equal to some output y of s divided by x of s. And what ends up happening is that we can actually model a differential equation from this. This just becomes s squared plus 2s y of s equals to s plus 1 x of s. Now, I won't discuss the property that I've used here, since it is in the realm of Laplace, but take it for granted that the result becomes the following: d squared y divided by dt squared plus 2 dy dt equals to dx dt plus x of t. And this differential equation is what allows us to model at least a transfer function given by this specific situation right here. But just in general, in the realm of control systems, if we are able to define a transfer function, we're therefore able to define a differential equation model for this. And that's what makes this extremely useful, because with a transfer function, we can ask about anything that we care about: stability, steady states, error, input, output, how to control the plant, how to adjust for the feedback, adding controllers, removing controllers, as well as even how to model a block diagram representation. We're able to ask everything given a transfer function. Now, there are multiple transfer functions. However, just for the scope of analysis, I will care only about two. One is called the closed loop. This is usually denoted by S, and that is given by the equation above. We also have the open loop, which is just asking about the forward times the feedback. And as such, we're also able to obtain the characteristic equation. 1 plus GH. This is mainly because this is part of the output. In theory, the output shouldn't change. And if it does change, then we have to get different characteristic equations at the bottom. But overall, for a transfer function, ideally, there is no change to it. And now we wrapped up most of the important parts of higher order differential equations. There are other parts that would have been discussed. However, within the scope of understanding the prerequisite, we only really care about why we need the complementary plus particular, as well as just going into higher order differential equations, because that is what models most physical systems. Everything else is variable, and as such, we don't mind it. Okay, thank you.